Now we start article thermodynamic equilibrium. Now what is thermodynamic equilibrium? A system is in thermodynamic equilibrium if the following three conditions of equilibrium are satisfied simultaneously. Now let's see the three conditions. When all the three conditions satisfied simultaneously, we can say that the system is in thermodynamic equilibrium. Now the first condition is mechanical equilibrium. Second condition is chemical equilibrium. And third condition is thermal equilibrium. When all these three conditions satisfied simultaneously by a system, then we say that a system is in thermodynamic equilibrium. Now here, one by one, let me try to cover what is mechanical equilibrium, what is chemical equilibrium, what is thermal equilibrium. Let me start with the mechanical equilibrium. Now, mechanical equilibrium. When there are no unbalanced forces within the system and between the system and its surrounding, then that system is said to be in mechanical equilibrium. Listen, no unbalanced forces means whatever the forces are there, that forces are balanced. Okay? No unbalanced forces in a system, then it is called as mechanical equilibrium. For example, if object is placed on table, it is at rest. That time, it is acted by balanced forces. The balanced forces are downward weight and upward normal reaction by the table. It is balanced forces. Okay, you remember here, mechanical equilibrium means in that mechanical equilibrium, there are no unbalanced forces within the system and between the system. The system is also said to be in mechanical equilibrium when the pressure throughout the system and between the system and surrounding is the same and does not change with time. Now let me define here mechanical equilibrium in terms of pressure. Generally, pressure is a variable. Okay? The system is said to be in mechanical equilibrium when pressure throughout system, between the system and surrounding is same. If pressure is same, we can say that a mechanical equilibrium is achieved. And pressure must be constant. It does not change with time, that you remember. Now next one is chemical equilibrium. I hope everyone understood what exactly mean by the mechanical equilibrium. You remember in terms of pressure, pressure is constant, then system is in mechanical equilibrium. Now second one is chemical equilibrium. Now what is chemical equilibrium? When there are no chemical reaction going on within the system, or there is no transfer of matter from one part of system to the other part due to diffusion. No chemical reaction, no transfer of matter from one part of system to other part, then it is in chemical equilibrium. A system is in chemical equilibrium when its chemical composition is same throughout and does not change with time. Means whatever we are using in a system, its chemical composition is always same. It does not change with time. Then we can say that the system is in chemical equilibrium. After that, the last one is thermal equilibrium. Now, what is thermal equilibrium? When the temperature of system is uniform throughout and does not change with time, system is said to be in thermal equilibrium. And temperature is constant and not changing with time, then we can say that a thermal equilibrium is there. Now let's see what is thermodynamic state variables. Thermodynamic state variables are pressure, volume, temperature, internal energy, and entropy. Now here everyone know pressure, volume, temperature, internal energy, and entropy. All the thermodynamic variables are representing in term of pressure, volume, and temperature. We discussed these three. And the internal energy. Means you know that internal energy depends on this temperature. So the relation we already covered in the previous lecture. For the different types of the process, the different thermodynamic variables are constant. Means type of the process also we have to learn. It means that for different type of the process, different variable are constant. Now, when pressure is constant, when volume is constant, when temperature is constant, what type of the process is there? That process also we have to cover. For example, so let's see one example here. Isothermal process. Isothermal process means temperature constant. Isobaric process. Isobaric means pressure is constant. Isochoric process. Volume in that isochoric, volume of gas remains constant. So here, for different type of the process, different variables are constant. Means if the word is coming isothermal, means temperature is constant. Isobaric, pressure. Isochoric, volume. Now let me learn equation of state. There is a relation between thermodynamic variables for a system is called the equation of state. The equation of state is completely defined in terms of pressure, volume, and temperature. The graphical representation of equation of state of system called PV diagram. The graphical representation of this equation of state of system is called as PV diagram, or it is also called as PV curve. It is also called as indicator diagram, PV curve, indicator diagram, etc. Now, when we are discussing any thermodynamic system, this PV diagram is playing a very crucial role. For example, for the ideal gas, thermodynamic equation is PV is equal to RT. So this is for ideal gas. PV is equal to RT. For isothermal process, it is, you know that T is constant, isothermal means temperature is constant, and this R is already constant. So we can write here PV is constant. Or in another word, we can write P1 V1 is equal to P2 V2. For adiabatic process, the equation of state is PV raised to gamma is constant. Now what is gamma? So remember here, gamma is ratio of specific heat. And ratio of specific heat for different kind of the gas, for monoatomic, diatomic, and polyatomic, we already obtained in a last chapter, kinetic theory of gases. So here, for adiabatic process, the equation of state is PV raised to gamma is constant. Or in term of temperature, when we are writing T into V raised to gamma minus 1 is constant. So gamma is ratio of specific heat, that everyone note. Now let's see a figure. which shows typical PV diagram for ideal gas at constant temperature. You can see this diagram. So here, this is P, pressure, and this is volume. So let's see the relation. So you know that for isotherm at constant temperature means isothermal, this is a relation. PV is equal to constant. P into V is constant. So the relation between P and V is inverse relation. It means that pressure increases, volume decreases. Okay? Or volume increases, pressure decreases. You can see from the relation here. So this is the initial position A. As we start increasing the volume, so we start increasing the volume, then pressure start decreasing. Okay? And when the final volume is V2, that time pressure is P2. You can see here, when volume is V2, pressure is P2, pressure decreases. So the Riti is indicator diagram. It gives idea about the system. Now let's see the PV diagram in detail. So you know that work done is equal to integration of P into dV. This formula we already obtained in the last lecture. So within the limit between initial volume to final volume. The integral in this equation can be evaluated if we know the relation between pressure, volume, or the path between the limits of integration. Now we consider here a gas confined to cylinder with movable piston. Movable, frictionless, massless piston. Piston must be movable, frictionless, no friction, and massless. We consider the ideal situation. Now, then we have to consider some cases here. We are expanding a gas with varying pressure. Means we are changing the pressure and that time we have to expand gas. Now after that, it can be compressed. Now we are compressing it with varying pressure. Obviously, when we compress the gas, pressure changes. It can expand at constant pressure. Means three cases here. First one, expanded with changing pressure. Again, compressed with changing pressure. Again, expanding with constant pressure. Okay, and all the three cases we have to show by a diagram. Okay, the area under this curve PV diagram is the graphical representation of the value of the integral. Since this integration, you can see this integration here. This integration represents work done in changing the volume of the gas. And if you draw the PV diagram here, P versus V diagram, and if you want to find out the work done, then you can find out area under that curve. Area under the curve also represent work done. Now let's see here. Now let's see the first point in detail. Gas expanded with varying pressure. When volume of gas changes due to outward displacement of the piston and the pressure of gas decreases. Work done by gas in this case is positive because volume of gas has increased. Now you know that when work done is positive, and that we already covered. Now pay attention here. When we are considering this is a gas, it is heated inside a container having a piston, massless, frictionless piston. So this is a gas. When we heat, the gas changes its volume and this piston moves outward. When we start heating, with varying pressure. So gas is expanded with varying pressure. Now here, as we heat it, then the piston moves upward and pressure, volume increases basically and pressure decreases. And in that case, you can see a diagram here, PV diagram. So this is the indicator diagram for this gas expanded with varying pressure. You can see here, so this is the position, initial position. Okay? And this is the final position. When we start heating gas, the piston start moving upward. It start moving upward. Means volume increases. Volume increases. You can see here initial volume is V1. As we start hitting, piston moves outward, volume start increasing, and it reaches to a final volume V2. As volume increases, pressure decreases. You can see here initial pressure P1 which is greater and P2 is less. I hope you understood this gas expanded with varying pressure. And this is a path. You can see here system changes from point 1 to point 2. And if you want to find out work done in this case, you can find out area of this portion. Area the graph under this curve gives us work done. If you find out area of this and whatever the area you will get, and it is equal to the work done. Now next is gas compressed with varying pressure. Gas compressed with varying pressure. Now here compression of the gas. So here it expanded, gas expanded here. Now here it is compressed. Now let's see the PV diagram for this case. So when compression of gas due to inward displacement of piston is moving inside, the pressure of the gas increases. Obviously the volume decreases means pressure increases, and work done by the gas is now negative. Now work done is negative. You can see diagram here. The same graph you can see, but here this is the initial position 1 and this is the final position. And when we find out a work done, we get same work done in both the cases, but here the work done is positive, and in this case work done is negative. Now in simple conclusion you can say that when volume increases, work done positive. You can see here the diagram. So here volume increases, work done is positive. So here initial volume is V1, final volume is V2. Volume decreases. When volume decreases, work done is negative. Listen, you can remember this. When we are solving problem, that time we must have idea what happened, what sign we have to take for the work done. When to positive, when to negative. Now the third case we can see here. Gas expand at constant pressure. So when volume of gas changes from Vi to Vf, means initial volume to final volume at constant pressure, work done during volume change at constant pressure is, so this is the formula for the work done. You know that work done is given by P into change in volume. So we already have idea work done is equal to integration of P into dV. Okay. So when volume changes by initial to final volume, so we can write here, if you don't want to use integration here, Vf minus Vi. Now you can see diagram here. Pressure is constant. So this is a pressure. Pressure having a fixed value. This is a pressure, initial pressure P. When the final position is obtained, then also pressure is P. But the volume you can see here, this is the first volume, initial volume, and this is final volume. So here volume decreased. Obviously here volume decreases, sorry, volume increases. You can see the diagram. Volume increased. And if you want to find out work done in this case, so you can find out area under the curve, and that area under the curve gives us work done. And this work done is positive. I told you when volume increases, work is positive. So here volume is V1 and then the final volume is V2, which is greater. So work done is positive in this case. When the volume is constant in any thermodynamic process, work done is zero. You note one here. Volume constant, work done is zero. Because you know that work done is equal to integration of P into dV. dV is the change in volume. So no change in volume means work done is zero. And you know that when work done is positive, when volume increases, work done positive. When volume decreases, work done negative. No change in the volume, work done is zero. Now next, we have to learn thermodynamic process. A thermodynamic process is a procedure by which initial state of system changes to final system. Just we already seen here different kinds of PV diagram in that initial state and final state. We already discussed. For example, when piston of cylinder is pushed in, some work is done. Work is done on the system. Such process in which changes in the state variable of system occurs infinitely slowly are called quasi-static. Means if the changes in the state variable, they are very slow, then that thermodynamic process are called as quasi-static. What is quasi-static system? Whose changes are very slow. When thermodynamic system changes from its initial state to final state, it passes through a series of intermediate state. Means any system we are considering the initial state to final state. So many systems, or it passes through a series of changes, series of intermediate states. This series of intermediate states, when plotted on PV diagram, is called path. Just we already seen here three diagrams. In that three different paths, 1 to 2, how it goes. Then again, means different paths we already learned. Now here we discuss some points here. Work done during thermodynamic process. You can see here, this is a diagram. Different way to change a system. You can see this is the first A to B. Listen, this is point A. Let's say initial point. B is the final point. Now we can reach B, means A to B, by different ways. By this is the first way, this is second way, this is third way. Means by different way, we can reach to the final state. Let me discuss one by one. Let us understand the relation between the path and work done. Now, what is the relation? This is path is 1, then how much is the work done in that? Path is 2, path is 3. Then what is the relationship between the work done and path? That relation we have to learn. You can see diagram here which describe different ways in which we can change the state of system. The system is initially at A on the PV diagram. The pressure is Pi and volume is Vi. You can see here when it is at A. So Pi is the pressure, initial pressure. Vi is the initial volume. We say that The state is indicated by the coordinates. Means position A is the initial position, can be indicated by coordinates vi, comma pi, x coordinate, comma y coordinate. The final state of system is shown by the point B with its coordinate. Similar manner, final state Vf, Pf, x coordinate and y coordinate. This figure shows many ways in which we can change the system from A to B.